is the Wasserstein space. One reference is the first book of Villani, Topics in Optimal Transportation, and chapter 7 specifically. So up until now, the way we talked about this optimal transport problem, we just presented it as we have this optimization problem between probability measures. We start with the Monge problem, then we relaxed it to the Kantorovich problem, then we talked about uniqueness, we talked about existence, we talked about duality, all these properties of optimization problems. The perspective that we take here is to use this optimization problem as a way of defining a notion of metric between probability measures. So we used to thinking about metrics on some fixed Euclidean space or maybe on a manifold, but now we want to imagine that we have the space of all probability measures over some, let's say, Euclidean space, and then we want to talk about that space as being a metric space with the metric coming from this optimization problem. Now, of course, there are many notions of distances between probability measures. To say how close two probability measures are to each other, there is no one unique way to do it. There are many ways. But this will be one way which turned out to be very useful for many reasons. So let me just start right away by defining it. Of course, you can do it in greater generality, but we'll focus on the Euclidean case. So the probability, maybe I'll write it here because we might need it for a while. So if we have two probability measures, mu and nu, and mu and nu will be assumed to be in, we use this notation as the space of all probability measures on Rn that have a p moment which is finite. We just want things to make sense. So the way we define this is exactly as a solution to the Kantorovich optimization problem. So it's an infimum over all coupling between mu and nu. And then we, for example, we can take, let me actually maybe do it just in the case 2, but also maybe 1. So we do x minus y squared, and then we do d pi xy, and then we take the square root. So this is obviously a non-negative quantity. If you have two probability measures, this is just the solution to the Kantorovich optimal transport problem. It will be non-negative. So far, we have no reason to think that this is really a metric. It's just some non-negative quantity that obviously captures how close mu and nu are because, well, we will check it later formally, but intuitively, if nu is equal to mu, you can see that this could be made to be 0. So obviously it captures some notion of distance between probability measures, but we want to argue that this is actually a valid metric. We can really view it as a metric on the space of probability measures. And the reason why this is a good notion, it's a good metric because it's a metric which incorporates the metric of the original space. Meaning here we're looking at our D and with its Euclidean metric, and that Euclidean metric has been incorporated into the definition of the distance between probability measures. And of course, we could have switched this by a different metric, and then we would have gotten a different type of distance here. So it's a way where other notions of distances between probability measures like total variation distance doesn't really, of course, you can rewrite it like that, but naturally it doesn't incorporate the geometry of the space. Although you can cook up a metric so that it becomes that way. Okay, so what we want to do today is we want to do 3 things. So one is to show that W2 is a metric on the space of probability measures with, let's say, finite second moment. So that's one thing we want to do. The second thing is to say, okay, now that we know that it's a metric, of course, it makes sense to talk about convergence in that metric. Like, what does it mean that a sequence of probability measures converge to a fixed measure with respect to that metric? So what will turn out is that convergence, or maybe I'll just say it, W2 metrizes weak convergence. So weak convergence, which I'll remind you what it is a very important notion of convergence in probability because, for example, for the central limit theorem, the sense in which some of IID random variables converge to a Gaussian, it's in the sense of weak convergence. So it's one of the most important notions of convergence in probability. And here W2 will metrize this notion, meaning that, roughly speaking, a sequence of probability measure will converge weakly to some measure if and only if they converge in W2. So we can think of weak convergence as just coming from this notion. And the last one would be linearization. So this means, imagine that we're in the situation where the measure nu is actually not that far from the measure mu. So, if you want to understand a quantity like that, it's good to do like small perturbation. So let's just write it like 1 plus epsilon times h plus then maybe we have epsilon squared terms times mu. So we have this h term which perturbs the measure nu from being mu, and then we would like to understand, so this would be presumably of order epsilon, but then times what? What is the first order coefficient? Okay, so that's the plan for today. Okay, so before I begin, are there any questions on what we've covered so far, or what we mean exactly here by talking about a metric space? Because that's, yeah. Oh, yes, thank you. Yeah, that's a good comment. I will try to do that. Other comments? Okay. So the goal for today is to construct this Wasserstein space, to say that we can talk about this space as a metric space of probability measures. There's a way in which we can say that there's a space of probability measures with a metric on it, where this metric is defined according to the solution of this Kantorovich optimal transport problem. And then we also want to investigate some of the basic properties of that metric. One of them will be the fact that it's related to weak convergence of probability measures. And the other one, we want to understand what is the linearization of that metric. Meaning, if I take 2 points which are very close, how can I expand, like do a Taylor expansion? Good? Okay. So let me start by, it's going to be a little bit of a recap, but plus an additional fact. Remember, in the previous lecture, Sinho showed us how to do duality. So this was the primal problem, and then it turned out that there were different ways of doing it, but one way it was to take the supremum over phi and psi, such that, I think we use this notation, phi, so this is phi of x plus psi of y is smaller than x minus y squared, and then you take the integral here of phi with respect to d mu, and then plus integral of psi with respect to d nu. Hopefully this is familiar. We had something like that. Then we saw that actually we can take psi to be the convex conjugate of phi and so on. So now I will just write as a fact. It's not too hard to prove, but it's a fact that will be important for us, that in the case where we take, so this was for general, so I will do it now for W1. So for W1, so I would remove it here, turned out that you can write this as a supremum over all functions phi, I will write like that, which are 1 Lipschitz. And I will remind you what that means, maybe with a minus. So what does it mean for phi? What does it mean that the Lipschitz constant of phi is smaller than 1? That's the same as saying that if we look at phi of y minus phi of x, the upper bounded by the, so here we're doing the L1 norm. So that's what it means for a function to be 1 Lipschitz. And the point is that you can replace the supremum in this problem by just taking a supremum over 1 Lipschitz function, where you take here phi d mu, and then here you have actually a minus in the integral of phi d nu. So it might not be obvious why you can kind of replace this class of functions here by this class of functions, but a little bit of an exercise to show that you can do it. You can ask me, maybe. If we have time, I'll show it, but I'm not sure if we'll have the time. But anyway, I would like you to remember that we have this form of duality as well, because that form will be quite important for us. Okay. So let's start with task 1, which is to show that W2 is indeed a metric on the space of probability measures. So I'm kind of switching here between 1 and 2. It doesn't really matter. When it's more convenient, I'm using W1. When it's more convenient, I'm using W2. But as you will see in the proof, everything which is true for one is true for the other, and in fact, it's true in much greater generality. Okay, so we have to check some basic axiom of what does it mean to be a metric. So the most basic one is that it has to be non-negative. So this one is clear just from the definition. It's clear that whatever probability measures you have, if you look at this quantity, this would always be non-negative. That's clear. We also need to check symmetry, that if we exchange the role of nu and mu, then we get the same result. But that's also clear from the definition of the distance. So that's okay too. The next one is to check that the distance between mu and nu is 0 if and only if mu is actually equal to nu. So one direction, well, both directions are kind of easy, but one direction is easier than the other one. So why is it that if we take nu to just be mu, why is it that we get 0? Anyone? If nu is equal to mu, why would we get 0 in that definition of the metric? So there's a general murmuration. You can do? Exactly. Exactly. You can just use the identity to transport both mu. So just write it out, because you can just take pi to be identity, comma, identity, push forward of mu. And when you take that particular coupling and you plug it into the definition here, you see that y is always equal to x, and therefore you always get 0. So that's why when we take mu to be equal to nu, we get 0. I should say that the reason why we chose to give this lecture, which is maybe a little more technical than the rest of the lecture and maybe not as fun, is to get used to just dealing with these objects. It's a good way of getting a little bit of exposure. So this direction is not hard. So that's good. But what about now? We need to show that mu that if we have that, then meaning if the W2 between mu and nu is equal to 0, then nu is equal to mu. So the way, sorry? Can you say it again? Yes, so exactly. We will use exactly that fact. So yeah, how do we show that? We use, as you say, because the assumption that the W2 between mu and nu is equal to 0, that implies, so this assumption implies that x minus y squared equals 0 pi almost everywhere, and therefore we can just say that pi is supported on the diagonal, meaning the set of points where x is equal to y. Otherwise, this W2 here is not going to be 0. So we know that. So why are we done? Well, now what you do is for every phi, which is a test function, what do we need to show? So if we can show that the integral of phi with respect to d mu is the same as the integral of phi against d nu, then we've basically shown that mu and nu are the same because we integrate against any test function. So that's what we're trying to show. So how do we do that? Well, just from the definition of a coupling, we can just write this. So I'll emphasize the role of x. So this is phi of x, and this is d mu of x. So we can write it as the integral of phi of x and then d pi xy. So just to make it clear, here the integral is over rd. Here the integral is over rd times rd. And it's always implicit, and the way you know what the domain of integration is, you just look at what's the probability measure that we're integrating against. That's how you know. Okay, but we just argue that because the W2 between mu and nu is equal to 0, we argue that it must be the case that pi is supported on the diagonal. So therefore, we can just write that d pi xy is d pi xx, because it's supported on the diagonal. But now we just exchange between the roles of x and y, and we write it as phi y d pi xy, but by the definition of pi being a coupling between mu and nu, this is the integral of phi of y against d nu of y. And therefore, we see that mu is equal to nu. Okay, so to recap the way the argument worked, we know that this is equal to 0. Therefore, from the definition, pi has to be supported on the diagonal, the set where x is equal to y. Once that is true, you just integrate phi against mu, and you express that in terms of integral against pi, because pi is a coupling, and then you use the fact that pi of xy is the same as pi of xx, and you switch, and you get the result. So that completes the part that shows that W2 between mu and nu is equal to 0 if and only if mu is equal to nu. So what's remaining to be shown? Yeah, so the triangle inequality is what we have. That's the last part. Okay. So we need to show that if we have mu1, mu2, mu3, then W2 between mu1 and mu3 is smaller than the distance between mu1 and mu2 plus the distance between mu2 and mu3. Okay, so that's what we need to show. So for that, we will use fact, the gluing lemma. I'll say in words how to prove it. If we have time, which I doubt, I'll write it down. But really, one can explain how to prove it in words. Let me first write what does the gluing lemma tell us. So what is going on here? Just staring at it, we can take obviously the optimal coupling for this W2, which couples mu2 and mu3. And similarly, we can do the same for mu1 and mu2. That's fine. But somehow you have to relate that to the coupling between mu1 and mu3. And that's not clear how this connection is going to work. So the gluing lemma says the following. So let pi 1, 2. So let me just make sure that I don't mess up the coordinates. So let's take pi 1, 2 to be a coupling between mu1 and mu2. And similarly for pi 2, 3, it's going to be a coupling between mu2 and mu3. So then the statement is that there exists pi, which is a probability measure which takes as input 3 coordinates, such that it's marginal. So I should write it a little bigger. on the 1, 2 coordinates is equal to pi 1, 2, and on the 2, 3 coordinates is equal to pi 2, 3. Okay, so this has nothing to do with optimality. This is just a general statement about constructing probability measures. So you start with a joint law between whose marginals are mu1 and mu2. Okay, so this is, and then you do the same. You have another joint law whose marginals are mu2 and mu3, and then you construct a probability measure on 3 variables such that if you look at only the first 2, you would get exactly pi 1 and pi 2, and if you look at the last 2, meaning 2 and 3, you get pi 2, 3. And the way you do it is, the way you construct this pi, I'll just say it in words, you sample x2 according to mu2, and then you condition on that x2, you sample from pi 1 to condition on x2 and pi 2, 3 condition on x2 independently. Yeah. Yeah, sorry, yeah, I realized, so that's why I removed the comma. So here I mean on the 1, 2 coordinate. So here, my notation is I don't use any commas. So what I'm saying is that if this is a measure now that has 3 coordinates, and I'm saying that if you look at only the first, so 1, 2 coordinates, so on the first 2 coordinates, it's going to be pi 1, 2, and similarly. Okay? So we're going to use this gluing lemma now to prove the triangle inequality. So the way we do it is as follows. So let's take now pi 1, 2, be the optimal coupling between mu1 and mu2, and similarly for pi 2, 3. This is between mu2 and mu3. And now let's take pi be as in the gluing lemma, and let's call pi 1, 3 the marginal of pi on the 1, 3 coordinates. Okay? So we know by construction pi 1, 2 is the optimal coupling between mu1 and mu2, and analogously for pi 2, 3 is the optimal coupling between mu2 and mu3. But this pi 1, 3, we don't know anything about its optimality, because we just constructed the pi from this gluing lemma using these 2 things as an input, and then we just call pi 1, 3, whatever it is, the marginal of pi on the 1, 3 coordinate, but we don't know anything about the optimality. Is it clear why the optimality is, it's not given? Okay. So now we can finish the proof. So let's see if we can try to do it together, if the audience is interested. So we're looking at the distance between mu1 and mu3, and we need to upper bound it by these 2 terms. What can we bound it by? Given all the construction that we have, I claim that there is one inequality that we know how to do. Exactly. Exactly. We can bound it by if we just look at x minus y, okay, yeah, let's do it like that. We just take the cost, and then we do it with respect to d pi 1, 3, because this is just an example of such coupling, but there's no reason for this coupling to be optimal. Let me just change the notation a little bit. So This will be x1 minus x3 squared d pi x1 x3. Okay, but from the construction of pi, yes, sorry, right, good, thank you. But from the construction of pi, we can now write with respect to the full measure, meaning x1, x2, x3. Where again, the integral here is now over 3 coordinates. We're just using the fact that pi 1, 3 is the marginal of pi on the first and third coordinates. Okay. Now we can upper bound it by x1 minus x2 plus, let's see if it's going to work. I think we need a square root here, probably. Sorry, do we need a square root?
No, you just apply because it's inequality with this.
I'm going to, right. Exactly. Later we're going to, well, we're going to apply Minkowski inequality twice. Okay, we can have the coordinates, the square, that's okay. Okay, the square roots. Okay. This should be the square root, no?
Yeah, so you just write x1 minus x3 or x1 minus x2 plus x2 minus x3.
Yes.
And then apply Minkowski's inequality
Yes.
with respect to pi.
Right, okay, yes, so we can do it like that. Yeah, so the point is, okay, so I'll skip that step, and we'll do it at once. So we'll get okay, we'll first do it with respect to pi, and then we'll do the x2 minus x3 squared. Okay, so here we used Minkowski's I guess L2 inequality. We don't need this. Okay, but now we can again apply the fact that the first and second marginal of pi are pi 1, 2, and similarly for pi 2, 3. So we'll have x1 minus x2 squared d pi 1, 2. And here we'll have x2 minus x3 squared d pi 2, 3. But remember that by assumption, this were actually the optimal coupling. So therefore, it's equal to W2 mu1 mu2 plus W2 mu2 mu3. So yeah, basically the key point was to say the key point for the triangle inequality was just to construct one particular coupling between mu1 and mu3 that even though was not the optimal one, it was such that we can relate it to the optimal coupling between mu1 and mu2 and mu2 and mu3, and the way we did it was via this gluing lemma. Yeah. Yeah, you're asking like how close is pi 1, 3 to the optimal coupling between, yeah. No, I don't think you can say anything in general because as I said, the construction of this pi, the way it works is you sample from x2, you condition on that, and then you sample from pi 1, 2 condition on x2 and pi 2, 3 condition on x2. But that thing you can just construct the x1, x2, and x3 so that it can deviate as much as you want.
You can take pi 1 and pi 3 the same and pi 2 different, and then pi 1, 3 of course.
Right, yeah. And you can make this arbitrarily large. Yeah. Okay, so that's a triangle inequality part, and therefore that finishes a proof of the fact that W2 is a metric. Okay, is there any question on that? Okay. Sorry? So it is because we made this assumption that mu and nu have finite second moment or p moment, depending. There are notions of optimal transport with infinite cost. Usually people don't, I don't think usually, well, okay, maybe they also work with things that don't have moments. Sometimes they work with just cost that can take on the value of plus infinity. And yeah, there is a theory for that. Obviously it's not as developed, but it exists. Okay, so for the next result, that one is the one about W2 metrizing weak convergence. I'm really going to be very lazy, and I'm going to take a very simplified setting. And to go beyond that simplified setting, there are just a lot of technical work and approximation, which I didn't think would be too interesting to show. Okay, so what is the statement that we want to prove? We want to say that W2 metrizes weak convergence. So here are the simplified assumption that we'll make. So rather than working with RD, we're going to work with a compact set of RD. And that's really going to simplify a lot. So we'll take X to be compact set of RD. And we'll also assume that the diameter, so the diameter is the distance between the 2 points in the set that are farthest away from each other. So we'll assume that the diameter is no more than 1. And we'll actually work in the we'll work with W1 instead of W2, but it's not actually a problem because you can show that all these W1, W2, WP for any P, they're all equivalent to each other up to some numerical constant. So the numerical constant, of course, is important in some application, but here, because we're just trying to show that it metrizes weak convergence, it doesn't really matter what the constant is. So the point is the W2 between two measures up to some constant, which can be very large, but it's equivalent to the W1 between them. So for this purpose, it doesn't matter. So we'll work with W1. Let me just remind you what is weak convergence. So we'll say that a sequence of probability measures mu k converges to mu weakly if the integral with respect to d mu k of phi converges to the integral with respect to d mu of phi for every phi which is continuous and bounded. So in our case, because, well, we said it's compact, so the continuous and bounded, you know. Yeah.
But this complete convergence actually, but W2, I think you are not defining it on the whole probability measure space. You are only defining on some kind of measure which integrates a finite number on the cost function.
Yeah, that's right. Exactly. Good. So good. So the point is, normally when you see the statement, if I understood you correctly, normally when you see the statement phrased, there would also be an assumption that there's some finite second moment for the measure. But I made my life easier by taking X to be compact, and therefore I don't have to worry about it. But in general, that's an additional assumption that one has to make. But it.
You also, this assumption also solves the difference between weak and.
Yes. Okay. That's yeah. But we're not even going to get to that, yeah. I really wanted to show this statement because it's a nice, another example of using duality, actually. So if you think about it, we're basically done because of the duality statement that I mentioned before. So, okay, so maybe actually, okay, I also want to write out what do I mean by Metrizes with convergence, just for people who are not as familiar. So what we mean by that is that W2 mu k mu converges to 0 if and only if mu k converges to mu weakly. That's what we mean by that. And why do we call it metrizes? Because the notion of weak convergence has nothing to do with any metric, right? When you just look at the definition, what does it mean for measures to converge to each other, for a sequence to converge to a measure weakly? It doesn't say anything about any metric or anything like that. But here, there's an actual, as we proved, this is a metric between two probability measures, and we're showing that this convergence is the same as that convergence. So in other words, the topology which comes from weak convergence is the same as the topology coming from this metric. Now, there are many metrics on the spaces of probability measures that would metrize weak convergence, meaning for which you will have this type of equivalence. Of course, we care about optimal transport, that's why we're focusing on this one. But the point is that it's a good metric because it's compatible with weak convergence. So if you wanted to show, for example, things like the central limit theorem, you can take mu k to be the law of a sum of k IID random variables normalized, and you will take mu to be the Gaussian, and then you will do some work to show that this converges to 0. Of course, you can use it because you know the central limit theorem, but that would be a natural way to proving that you have a central limit theorem by looking at this type of metric. Is it clear? Okay, so so really the point is, so the proof is, okay, we're not going to do all the details, but you just have to remember it's really by duality. So just remember that we wrote, so again, we're going to focus on W1. So remember that we can also write as a supremum over all these functions which are Lipschitz with constant 1. And then we write phi d mu minus phi d nu. But then the point is, because we have this representation, Lipschitz functions are going to be continuous, so therefore you will get weak convergence, and if you wanted to go the other way, you will just approximate general continuous functions by Lipschitz function. So it would be an approximation argument. So to go in one direction, it's easy, meaning if you have this, then you know that because Lipschitz functions are continuous. Sorry, so that shows us this direction. So if you know weak convergence, in particular, we apply it to Lipschitz function, and we'll get this. And if we want to go the other way, we will just show that continuous function can be approximated by one Lipschitz functions. Of course, this is just showing for the special case where the diameter is upper bounded by 1, it's compact, and if you want to go to the general case, there are many, many approximation steps that one has to make, so the proof is quite technical. That's kind of the basic idea behind it, and it's a nice way of showing how duality comes into the picture. Good. So what I'm left to do is linearization, which is a little more fun, I think. Any question before we continue? Yeah.
So is this any kind of duality for W2?
No, this is for W1, this particular duality. But you can get similar type of dualities for other costs, but this particular one is for W1. But again, because for the purposes of metrizing weak convergence, you can work with either metric, because the idea is, because when you change from W2 to W1, they would change only up to constant. If the sequence converges in one, it would also converge in the other, because you just multiplied by some constant. That's why it doesn't matter for this purpose which metric we work with exactly.
Yes, it seems to me that the triangle inequality is followed directly.
Oh, you mean that you would have another proof of the triangle inequality for W1 using duality? Is that what you're saying?
Yeah.
Right. Yeah, I guess. Yeah, I think you're right. Yeah, there is okay. Right. So linearization. So linearization. We're trying to understand what can we say about the distance between mu and between a perturbation of mu. So what's written here is 1 plus epsilon h for some function h plus O of epsilon squared. So without this would just be 0, but now we have some perturbation. So what we would like to understand is we want to express that as epsilon times some quantity which presumably should depend on h somehow. Right? The question is what? What is this going to be the quantity here that will depend on h? Well, what would it be? Okay. So in order to understand that, here's an exercise which I very much recommend you do.
What is h?
H is just some function that you take in order to perturb the measure mu. That's like your perturbation. And we want to express that and say that, okay, the distance between mu and its perturbation is of order epsilon, and here there should be a coefficient which depends on h somehow on the perturbation. And the question is, what is it? Yes?
So it's still a measure.
Yeah, of course, yeah. We assume that we do it in such a way that this is still a measure. Yeah. A probability measure, yes. So I'm being formal here. Yeah, this would not make sense otherwise. So that's why there's the epsilon squared, to make sure that this is actually everything. But also you have to choose the h so that it's a probability measure. Okay. So what is the exercise? The exercise is as follows. Suppose you have d mu, which let's say mu and nu have densities. Okay? And exactly we will assume that G is a perturbation of F. So 1 plus epsilon H plus O of epsilon squared times F. Okay. And we will make the ansatz that the Bernier map, remember we had this Bernier map from the previous lecture for W2 that mapped mu into nu, and it was a gradient of a convex function. So because we assume that nu is very close to mu, we expect that the Bernier map to be very close to the identity, because we assume that nu is just a small perturbation of mu. So let's write phi of x as x squared over 2 plus epsilon psi of x plus O of epsilon squared. So what is going on here? If you take the gradient of phi, the first term is just going to give you the identity, and that captures the fact that this Bernier map is almost the identity because nu is almost mu. But then there's some correction, and we just call that correction psi. Okay? So this is a setup, and here's what you need to show. Show that L psi is equal to H, where L is minus the Laplacian minus the inner product between the gradient of log f and the gradient. So this is a differential operator. So what we mean by that if we apply it to a function eta, L of eta is equal to minus Laplacian of eta minus the inner product gradient log f gradient eta. Okay. So L is a differential operator. In fact, the differential operator that will come up in the previous lectures quite often. This is related to the Langevin dynamics, which we'll talk about. But for now, it's just some differential operator, which is related to f being the density of mu. And the claim is that the connection between this part of the transport map, this psi, so psi is a part of the transport map which has to do with the perturbation. That's a part which is not the identity. The relation between psi and h, which is also the part of g, which is being perturbed for being f, is exactly according to this linear equation. So, of course, it's a very natural question. You ask yourself, if nu was just equal to mu, meaning if g was equal to f, then the Bernier map would just be the identity. That's trivial. Suppose I perturb g by this function h, how does my transport map get perturbed as well? What's the relation between perturbing the measure and perturbing the transport map? This claim says that the relation between them is linear. It's an infinite dimensional. You can think of it as a matrix equation. It's just a kind of an infinite dimensional matrix because we have this operator L, but we have this linear relation between the perturbation of the transport map psi and the perturbation of the measure mu, which is described through h. Yeah. So I'll just give you a hint how to do it. So you should recall this change of variables formula that we did for transporting between one measure to the other. Remember that we had f of x is equal to g of gradient phi of x, determinant of Hessian of phi of x. I'm not putting the absolute value because now we know that it's convex and therefore it's positive semi-definite. So this was true for any transport map. So now you should just take phi to be this phi, and you should take g to be this g, and then just expand everything up to first order in epsilon and find out that you have this relation. So this equation is the linearization of the Monge-Ampere equation. This is called the Monge-Ampere equation. Okay. And of course here you will use the fact that, if you don't know, like if you take the determinant of identity plus epsilon something, you can express it in terms of the trace. That's like a Jacobi formula. So we will use this exercise in order to understand the distance between mu and its perturbation. Do I have only 5 minutes? Is that right? A little more? Okay. All right. So we'll see how much we can cover. So here is a dilemma, which tells us how to relate the two. And the claim is that if we look at W2 between mu and then this perturbation, then, okay, maybe we'll look at the squared. Then it's equal to epsilon, the integral of h, L inverse h d mu, and then there are epsilon order terms. So L inverse just mean, again, this is the inverse of the operator. You can just think of it as the inverse of a matrix. Just think of this as a matrix which maps a vector psi into a vector h, so L inverse is just its inverse. Okay, yes, sorry, because I squared. Okay, so let me actually write it as like that because I want to emphasize it. So, thank you. Okay, but actually, if you stare at it for a second, you will see that it's an immediate consequence of this exercise. Why? So, what do we know about? So I will just, from now on, ignore all these O of epsilon squared terms. So remember that if we use the Bernier map, this is just x minus, so this is just the Monge problem, right? It's x minus a transport map at x, and then we integrate with respect to the mu. Is this equality clear, this one? This is just because we know that the optimal transport map between these two measures was used. We're just using the Bernier map. Okay, for now I haven't used anything, but now I will use the fact, which I'm just taking it as a granted, that you can always write phi in this way. So if you can write phi as x squared over 2 plus epsilon psi, when you differentiate, this term just becomes x, and it cancels with this x. So this is equal to epsilon squared, the integral of gradient psi squared d mu. Okay. But what can we do now? We know from the exercise that psi can be written as the gradient of L inverse of h d mu. This is from this relation here. So we're getting pretty close. So in some sense, you could say I could have stopped here, because the original goal, like we said, we wanted to find an expression for the distance between mu and its perturbation just in terms of h, right? That was what we wanted. And in some sense, you could say, okay, we kind of have it here. We have the gradient, we have h. Okay, you apply L inverse to it, but that's fine. So we can stop. Any idea how you go from here to here, maybe? So there is a nice book by Bacri, Gentil, and Ledoux, which is like 500 pages. And then at the beginning, it says, how far can you go with Cauchy-Schwarz inequality and integration by parts? And the answer is you can go as far as 500 pages. So this is a good example of maybe the baby step in this 500 pages is like integration by parts. So this actually follows from integration by parts. So what we're using here, this is, again, another exercise that if you look at H1, L, H2, first of all, you can put the L on the H1, sorry, d mu. You can put the L on the H1, it's okay. But here the integration by parts, you can actually write as gradient H1, gradient H2, d mu. Okay, this you prove by integration by parts. And now, because we're running out of time, I'll just say that you use this in order to get what we want, except that, without the square root in epsilon squared. And the way you do it, you just insert L again, right? You have L inverse, you can write again L inverse, and then you do the integration by parts, and that's how you get it. Actually, unfortunately, we're out of time, but here, I just wrote it as, the way I pitched it, I said, we know that this measure nu is a perturbation of mu in terms of h, so you want to find an expression which depends only on h, and okay, good, we found one. Actually, this can be viewed as a norm, and it's the dual norm of a norm which just captures the gradient of h, but unfortunately, I don't have the time to show it, but it's not hard. But the point is that this is not just an expression which depends on h, it actually has the interpretation of a norm. So we can say that the first order term in the expansion of the Wasserstein distance in terms of epsilon is this norm of the function h, where the function h comes from the perturbation. And at the step here, you use this integration by parts formula, which the way you prove this, you just do integration by parts, which I highly recommend doing. Just remember, L is the expression here. Okay, so I think I'm out of time, so I'll stop here. Okay.
Any questions? Can I ask, so is it true that everything before linearization basically holds for WP, but this part heavily depends on...
Yeah. So the fact that it's a metric, it holds even for much more general cost, assuming they're coming from a metric. the metrization of weak convergence holds for WP for every P. Yes, this is now special indeed to W2, and of course it's special like here we use Bernier theorem, which normally we wouldn't really have, right? If we took, instead of W2, if we took different Wasserstein distance, we would not be able to write the solution of, to write this Wasserstein distance in terms of like a Monge problem. We don't know that there is an optimal, not necessarily depending on, yeah. So this one is special.
In view of the time, let's thank Yair again.